Well, thank you. Also, thank you, QX, for the opportunity to tell something about qgym. Yeah, it's a great opportunity to share something about what reinforcement learning can mean to the world of quantum computers. And today I will show you a bit about what we have built. It's the qgym, and it's a gym to train and benchmark reinforcement learning based quantum compilation. I do this together with Sebastian Veld, who is a professor at the TU in Delft, which is a technical university in the Netherlands. And with my colleague Stan and former colleague Tanik, we built this gym. And QTech, who is the owner of this gym, is a collaboration between the Technical University in Delft and TNO. TNO is the Applied Research Institute of the Netherlands. Okay, so what will I be talking about? First, I will give a bit of a background, both of what reinforcement learning is about, and also how can you look at the compiler. And then this will be the stepping stone for telling about how you can combine these two subjects. Then I will share something about the goal of why we built the gym at first, and now also about how it is developing. I will give a short overview of how the gym is structured and how you could work with it. And before wrapping it up, I will show an example of how you can apply reinforcement learning to the act of routing. And there I will also highlight a bit of how people can play with our gym to see how they can improve the compilation. And we will wrap up with what's ahead. Okay, so let's start. What is a quantum compiler? Basically, we all know what the quantum circuit is. It's just the qubits with the gates and operations between gates. And somehow you want to run this circuit on quantum hardware. And the quantum hardware can vary a lot in terms of topologies, in terms of fidelities, in terms of operation times, and really hardware-specific things. So the generic quantum circuit always needs something in between, which is the quantum compiler. And basically every computer or many things in the world have a compiler to go from the generic case to the specific implementation, and the quantum computer also has this. And our goal with the qgym is to improve this bridge. If you look inside a quantum compiler, you can see it as a set of passes or a set of functionalities. And a compiler always has a set of functionalities which it has to apply before the compilation is ready to execute some code on the actual device. And some of these passes are easy. If you have a certain gate, I think this is a C0, and then you need to compose them such that they can be decomposed into the native gate set of the actual device. This is a really straightforward task, and this can be done once the native gate set is known, and how to convert every gate that's not in a native gate set to this native gate set. However, there are also some passes that are really difficult. And one of these things is the initial mapping. So this means if you have the logical qubits in your quantum circuit and you want to map them onto quantum hardware, you need to choose which logical qubit in your circuit will correspond to what physical qubit in your quantum hardware. And the problem itself seems really easy, but to do this in an optimal way is really hard. And the mapping also really implies a lot for how the routing has to be done and how all the operations on the device have to be scheduled. So this problem is NP hard, and therefore it's really suitable to try different methods to solve this, because NP hard problems are not solvable in polynomial time. So either if you want to solve this problem, you need some heuristics or some other methods to do it. Well, what do we then focus on? So we focus at this moment on three passes, namely the mapping pass, the scheduling pass, and the routing pass. And we try to improve these difficult passes with reinforcement learning. So what then is reinforcement learning? Okay, so imagine you have a maze, which we call the environment, and you have a software agent, which is this nice emoticon on the slide. And an agent can observe something. For example, the agent says, I observe one wall behind me and the other spaces are free. So on the left, on the right and up, the spaces are free. And the agent has to decide what to do. And we say that the goal for this agent in this example will be to find a way out of the maze. And it does this by observing, then taking an action, and every time it has done an action, it will get some kind of a reward, or maybe after it has finished the whole process of getting out of the maze, it will get a reward, or you can sometimes also do it step by step. And if you then give an agent a lot of different mazes, and every time you give a certain type of a reward, so if it does it very quickly, you give a good reward. If it does it slow, you give high punishments. Then the agent can learn through this reinforcement process, the process of penalizing and rewarding. It can learn to execute this task. Well, then what is the goal of the quantum compiler or the quantum compilation gym? You can compare it with the human gym. In a human gym, people are pushing heavy weights, doing tough tasks, and sweating to get stronger and to be able to either push heavier weights or push it more often in the same time. And you could say about being in the gym, it never gets easier, but you just get stronger. And it's also when you're running, they say it never gets easier, but you just go faster. And same holds also for reinforcement learning. The agent will try to learn these tasks, and hopefully it will learn to do it faster than existing heuristics or other types of algorithms. So what does the gym consist of? In a human gym, you have a collection of training equipment, and in the reinforcement learning gym, you have a collection of training environments. And the training equipment in a normal gym is standardized. It's such that people know how to work with it. And that is really accessible for many people. And in the same way, we want to have a standardized API so that it's easy for many people that are developing quantum algorithms or look at the process of quantum compilation, that it's intuitive for them to work with it. Then why do we want the gym? First of all, we want the standardized API, and this had a reason also in the Netherlands within QTech. What happened a lot was that the actual compiler of the device in the Netherlands was written in C++, and the language was not really accessible. It had a lot of internal optimizations, and sometimes people try to extend the compiler by adding some components or functionalities, and by doing so, a lot of researchers, different researchers or developers, got a lot of incompatible compilers, which were hard to merge, and this caused a problem in the development of the whole stack. And we basically want to prevent this with the gym. So we want to avoid that you have multiple non-compatible compilers. And instead, what the qgym aims to do is it aims to be to abstract away all the irrelevant parts so that it's really accessible for many different types of researchers or developers, and that's what you get out of the gym, namely eventually a trained agent that you can apply it to the device of your desire. So you can incorporate it in a compiler which you would like to work with. And the development, how we have done it is, it consists of general building blocks, so it's easy to add extra components, and consists of some visualizations and tools that make it easier to work with it. Well, then what does the qgym consist of? You can describe it quite compact. It consists of environments, namely the initial mapping, the scheduling, and the routing. And we have some templates. All the environments are built from a certain template. And if people want to play with it, they can build their own environments, or they can tweak existing environments in their own fork of the gym. And currently we're working on benchmarks. So what this will include, or what we try to help people with, is once they have trained an agent, they want to see how does it perform and how does it compare to existing compilers that do these specific tasks. We want to help them with that. Moreover, training also really depends a lot on what training data you put in, and somehow we also want to make it easier to make choices for the set of training data, because you can train a reinforcement learning agent on randomized data sets, but also on specific data sets or semi-random, and this impacts the performance of your agent. Well, we have a couple of design principles. First of all, it should be easy to use, and that's the case currently. You can just install the package and initialize an environment with a couple of lines. It's really customizable. You can customize your environments to your desire. And an important role in reinforcement learning is what kind of rewards you choose, and you can make your own reward functions or adjust existing reward functions. And yeah, as I said, you can also add your own environments. And it's platform independent. So yeah, we think it's quite accessible. And now I would like to go to an example. So how does the environment, how does qgym work in practice? As an example, we will look at the process of routing. And what routing is about is, okay, you have the quantum circuit, and if you look at the quantum circuit, yes, if you look at the quantum circuit, you will see that there are three gates that are applied between two qubits. Namely, you have a gate, first of all, between qubit 2 and 1, then between qubit 1 and 0, then between 2 and 0. And for this very small example, we consider a hardware topology where you have 3 qubits with a length between 0 and 1 and 1 and 2. And if you want to execute this circuit on the topology, you will not be able to do it straight away because there is no link between qubit 0 and qubit 2. So what you need to do is to place a swap somewhere. And you can do it in this case by placing a swap between qubit 0 and qubit 1. And it will change the basically which logical qubit in your quantum circuit you relate to the physical qubit in your topology. And we have built an environment so that reinforcement learning agent can learn to place swap gates, and ideally to place as minimal swap gates as possible. So here in this animation, you see basically an agent at work. The white part is the part that the agent can see. We say, let the agent have an observation space of a certain number of gates ahead. It's not important per se for the agent what the gate is. It should apply, but it's only important between which qubits the gate should apply. So you see lines between qubits and not what gate it is about. And if you look now, there is a red line. This means that with the current mapping, this gate could not be executed. And then if the reinforcement learning agent tries to pass this gate, meaning that, okay, it could be executed, it will be penalized because it cannot be executed. So then it is forced to place a swap gate until it can pass the gate. And every moment in time, it has the choice to either place a swap gate between some of the qubits or to go further. And if it wants to go further, but it cannot go further, it will be penalized. And it will also be penalized for placing many swaps. And basically, this very simple way of looking at the problem, the agent should, in an iterative way for many different circuits, it should learn how to map it optimally or to route it optimally for this given topology.
All right. Yeah, Willem, thanks so much. We do have a bit of a tight schedule here, so we're going to just need to keep the show rolling here, but really appreciate your talk. Again, for everybody in the chat, Willem will be on the Discord as well. So if you have any questions for Willem, please head over there, and that's where we'll continue the talk. Just maybe one quick question, actually, Willem. I'm curious, do you have a background in computer science or in quantum or physics?
I have a background in mathematics and physics, but yeah.
Okay, well, nice, cool. Well, Willem, thanks so much for joining us here at QHack. Really appreciate your talk, and I am Dutch. Let me just see if I can get this right. Dank u wel and tot ziens.
Yeah, Zeker. Bedankt.
Awesome. All right. Thanks. Goodbye.